Okay, so welcome to this talk about Sambamba, our runtime system for online adaptive parallelization. And of course, it's based on LLVM. So what I'm presenting here is joint work together with my colleague Kevin Streit, who is also here, as well as Sebastian Hack and Andreas Zeller, all from Saarland University in Germany. And the problem that we are trying to tackle in this project is porting legacy code, which has been programmed for sequential execution, to modern hardware, which typically consists of multiple cores. And of course, you want to leverage this computational power. So when you, as a developer or also an automatic tool, does this parallelization, it or you have to not only to find the parallelizable code locations, you also have to decide if and how to parallelize those. So if we take, for example, an application which iterates over a data structure and processes the elements, then if you know that the processing of the individual elements is independent from each other, you might want to distribute them to different threads and get a scalable speedup from that. If, on the other hand, you know that the processing of the individual elements is a quite complex task and you can split it up in several independent smaller tasks, you might also want to parallelize the processing of each individual element. But which of these parallelizations or which combination of those is profitable depends not only on the input that you give to the program, it also depends on the target machine on which you're going to execute the program in the end. And this not only includes the number of cores, but also things like memory latency or inter-processor communication cost. So this is very hard to predict statically. And also in previous work, we have shown that even if two parallelizations are profitable in isolation, then the combination of both might be much worse. So we don't want to do these decisions statically, but we want to have an automatic approach which adapts to both the input and the target machine while the program is running. So the design in order to achieve this starts with some static analysis conducted at compile time. So here we analyze the data dependencies in the program. This is based on the well-known data structure analysis from the PoolAlloc project. From that, we generate the program dependence graph, and on this program representation, we pre-compute local parallel schedules. So these are schedules for small fragments of individual functions. And all this information that is pre-computed is then transferred to the runtime of the program where the actual parallelization happens. So here we combine the pre-computed local schedules to form whole parallel functions. And based on some heuristics, we might even decide to generate several variants of an individual function, which might then be tuned for several inputs, for example. Next, we bring all the created functions to execution by directly injecting them into the application, which is being run in a just-in-time compiled environment. And for those functions where we have several variants, we also install a dispatch mechanism which decides on each call which of the variants to use. Now we still have to make this adaptive, right? So what happens next is we profile the application which is running. So not only the execution time, but also branch probabilities, which technically also includes loop trip counts. And this information is then used in the next stage, which closes the cycle. So in this adaptation phase, we are re-evaluating the parallelization decisions that we have taken earlier. So this is the phase where we can react to changes in the input or changes in the execution environment, which manifest in changes in the performance of individual function variants. So the adaptation phase might decide to drop function variants or trigger the creation of new ones. So overall, this forms a cycle which continuously monitors the application and adapts it to the current execution situation. And all this happens while the program is executing. We also have some performance numbers showing that we indeed find good parallel configurations for most applications. So if you want to see or discuss those or anything else about Sambamba, you can come to our poster session where we show much more details about Sambamba. So yeah, that was Sambamba in a nutshell, and thanks for your attention.